Are there any questions? Did you say you had a question?
I said there's always questions. I watched your video where you talked about when a ball is kicked, the equal force on the foot is equal force on the ball
In magnitude.
in magnitude. So, okay, and only in magnitude,
The directions should be opposite directions.
opposite directions, okay. So, for the like homework, the master set, it talks about a large truck riding with a small compact car, so that would be like the same scenario?
Absolutely.
Okay,
So it's same magnitude, opposite directions, same type. So normal force,
okay,
weight. I mean, it's whatever the force is being exerted, it's the same type of force.
okay. So it wouldn't be weight, it would
No.
be normal force?
It'd be normal in the case of kicking the ball.
Okay, but with the car and the truck, it would just be normal force?
It'd probably be normal force there too.
Yeah, because I would think the car would weigh less than the truck, big truck,
Presumably.
presumably. Yeah,
Yeah, but the force is still the same, either way.
okay.
Yeah. Classic Newton's third law. I was done with what I was saying, that you have the look of, there's a follow-up question, or
But
I didn't quite answer it.
I guess I'm just confused, because when I think of a car and a truck colliding, I think of the truck pushing the car because of the weight. Is that has to do with acceleration,
Yes.
so that's a different,
Yeah, that's sort of bringing in Newton's second law. If you're driving down the highway and you hit a bug, you exert a force on the bug exerts a force on the car. They're normal force presumably, and equal in magnitude. But because of the mass of your car is so much bigger, you don't notice it.
okay,
But the force is still there.
it's still there.
So when I drop an object, the earth does respond and the earth does come up, but it's so small because the earth is so massive, we don't notice it.
Right, so that has to do with normal force.
And that's good
That-
for whatever force happens to be involved. In the case of the dropping something towards the earth, that's the gravitational force. Car and truck, that's
That's
most
the
likely a normal force.
Because it's going
Yeah.
parallel to the ground instead of. Yes.
Yeah, or they're not, I think I said head-on collision.
Yeah, you did.
Yeah, so they're not scraping next to each other, in which case there'd be some friction involved there too.
Yeah.
Other questions? Seems that we were talking about momentum, that was the last thing. And we got as far as the formula for momentum, and we did a perfectly inelastic collision. In other words, two things hit and stuck to each other.
Mhm.
That one's pretty five, let's break it, right, 6. Interceptor, Mad Max reference. Anyway, what is the total momentum of the system? Somebody describe how you go about actually finding the total momentum. What are the steps?
Multiply,
Multiply what?
your kilograms and your meters per second.
Okay. So if you do that, what do you get?
You get 15 for the interceptor and 12 for the middle.
All right, so big thing is you're doing mass times velocity, and you have to do it for both objects. So we had, so the momentum here is 15 Newton seconds, and over here, 12 Newton seconds. All right. So the question was, what's the total momentum of the system?
Add them together,
Yeah.
so 27.
Yep.
Why are they considered a system?
Why is it considered the
Yeah,
system?
because to me, it looks like two different separate systems.
And, yeah, and properly I should have said, we have a system with these two objects in it.
Okay.
So, yes, the system could be whatever you define it to be. My intent was they are part of the same system. Because I want to make this a closed system, and so that momentum is conserved. So, P initial is just the sum. So when the interceptor catches up to the villain, he rams into the back of it, into the back of the villain's car. In this really low-speed chase, you probably walk faster. What's the total momentum of the system then?
Can you repeat it?
What, so the interceptor's gonna smack into the back of the villain. When they collide, what will be the total momentum of the system then?
27 newtons per second.
Yeah. Say it one more time.
27 newtons per second? Newtons.
Newton seconds.
Okay, newtons second.
All right, so that's gonna be P final. That's the whole idea of conservation of momentum, that whatever total I start with is what I end with. Unless the system is open and I've got some other thing involved here. If they stick together, well, then it's one object. It's still the final mass times the final velocity. What would the final mass be? If they stick together? Yeah. Times the final velocity. So my problem is 20, this is the math problem, 27 equals 9v. That's the math problem I'm working with. What is the final velocity? I think I heard 3. Let's finish it up. Like you mean it. All right. And again, the nice thing about this is we don't lose information on direction. We got a positive answer, which means they'll be going to the right, which makes sense if they started out going to the right. And yeah, positive answer, moving to the right. We don't care about what's happening before, right? We don't care about what happens while they're getting up to the same speed, because the 6 kilogram mass needs to speed up, the 3 kilogram mass will need to slow down, but in the end, what's happening during that range, we don't care about, just what happens at the beginning, what happens at the end.
So could we just subtract 5 minus 2? Or it just worked out that way?
Oh, just worked out that way.
Okay.
Yeah. 4 choice of numbers there.
Could you explain how you got 3 again?
I know that the total momentum after the collision is the same as what we started with. That's the 27. And that's gonna be equal to the final mass times velocity. It's one object, so 9 is the mass, 9 kilograms. And so 27 is equal to 9 times whatever the velocity is. This is, momentum is mass times velocity. I feel like that didn't quite catch what you're looking for.
Say it one more time.
All right, I know momentum is mass times velocity, because the powers that be said it that way. We got this by doing mass times velocity,
Right,
plus mass times velocity, and then the total is just the sum.
right.
In a collision, in a closed system, and I mean by closed system is that there's nothing from the outside, there's no extra object that don't know about or not caring about involved. So that's gonna be my total momentum afterwards. Well, if they stick together, it's now one object. And so that momentum's gotta be equal to mass times velocity. Again, where, since it's one object, it's just one mass times velocity.
Right.
And that one mass, well, I have 3 kilograms and 6 kilograms, when they combine, it's now 9. So 9 kilograms times the final velocity is gotta be equal to 27.
Oh, yeah. Okay. I get it.
Okay. So there are 3 and 6. I'll stick with the same initial scenario, 5 meters per second and 2 meters per second. Except this time, they're not sticking together. The 3 kilogram mass is gonna bounce backwards at 2, well, let's do a number we're not using, at 4 meters per second. And the 6 kilogram mass is still unknown. So the question is, what is its final velocity? And you start out the exact same ways you did before. What is the total momentum of the system? Again, assuming the system is comprised of those 2 objects.
27.
Yes, because the opening scenario hasn't changed, so my initial velocity is still the same. What's my final momentum? In unison would be really cool right now.
27.
Yeah, that's closer to unison than before. So that's my final. I can't just do it times the total mass times velocity because they're not together, so I have to break them down. What is its velocity, what is its momentum after the collision? Yes. Recognize that when we established that was 15 and 12 over there, we established that to the right was positive. So we have 27, establishing that is positive. So this is negative 12 Newton seconds. So I have 27 is equal to negative 12 plus whatever the momentum of that is, P6 final. So what is the momentum of the 6 kilogram mass? Yep, add 12 to both sides. So my final momentum of the 6 kilogram mass is 39 newton seconds. And that's gotta be equal to its mass times its velocity. 6 kilograms times its final velocity. So the math problem we're working with here is that 39 is equal to 6x, that's the math problem. So what is x? Or the final?
6.5.
One more time?
6.5.
Yes. So in the context of this is 6.5, what?
Meters.
All right. So conservation momentum, very powerful tool for predicting.
Above the 6.5 that you just wrote down, or the one below, to the left a little bit, that one, above that, velocity, what is that?
That's a 6 in F for
Okay,
the
gotcha.
velocity, final velocity of the 6 kilogram mass.
Gotcha, okay.
Okay. And by making that 6 clearer, I've actually made it worse. That's a 6.
And what is next to the 3 kilogram mass?
Here,
Yes, next to it.
that right there,
No.
that's
Right there.
4, that's a 4 meters per second.
Oh, okay.
And let me make it worse by trying to draw it. Oh,
And
that's so much better.
did you just put the 4 there, or did that come from somewhere?
I just put it there.
Okay, okay.
In physics 151 and 251, I would tell you how much energy was lost and you figure that out for yourself. But I will spare you.
Yes.
Unless there's popular demand, we can do it.
I'm so sorry, I'm not understanding why it's -12 and not -15.
Because after the collision, I said it was going 4 meters per second to the left.
Okay,
And the mass times velocity, the mass is 3, the velocity is 4, -4. That's why -12 comes from.
thank you.
And then, so because you didn't put the final velocity for the 6 kilogram, like the direction, I guess? Is that what we're looking for?
Yeah, that was what we were trying to find.
Okay, and then how does that result into the momentum initial, how is it 27 again?
In a closed system, and again, I have just these 2 objects, there's nothing else, there's no planet nearby, it's just these 2 objects. In a closed system, momentum is conserved, which means whatever my total that I begin with is the total I have at the end.
Yeah, I understand that,
Okay.
but you changed you changed it essentially because the direction and the velocity. That's why I was confused on how you still got 27.
Oh, so all right, it's gonna be 27 regardless of what I do right here.
Oh, okay, that's,
That 27, since that's my initial, as long as it's a closed system, doesn't matter what I write next, that's my final.
oh, okay.
So that's coming from just, ignore that. And then to break it down, I know it's also the sum of this plus whatever it is for this. Have to add up to 27.
Oh.
Yes?
How did you get 39?
Looking at this problem down here, I know that 27 was the -12 plus whatever this is. And so I have 27 equals -12 plus an unknown,
Oh, okay.
add 12 to both sides.
Thank you.
Other questions? Now, I will tell you that this scenario right here cannot happen. But the question is why? Oh, the steps, the process is absolutely spot on, not a problem with that. I'm not gonna suddenly go, oh, here's a mistake. No, the process we set up is correct. But before we really get into why can this not happen without an explosion or something like that, we need to talk about energy. So it's gonna shift away from this, talk about energy, and then we'll come back to it. So that was chapter 6, so chapter 7. Here we go. Now, much to your delight, I'm gonna do a derivation. A lot of letters. The main purpose for my doing it, again, is to show you that the stuff comes from somewhere as opposed to just sort of throwing up a formula onto the board and going, hey, just trust this works. So for some of you, follow along. For some of you, sort of let it flow. But if you recall that exercise I went through where I had the two objects colliding, what are the things that were true for both of them? When we did force times time, we ended up with momentum. We're now doing force times displacement. So I'm going to start out with, I have some force on an object, object A, caused by object B. Again, this is the force on A from B, times the displacement of the object. All right, dot products. We talked about dot products or not?
No.
We did not. Okay, that was a very emphatic no. Let's talk about dot products. When you're multiplying scalars, that's the math when you first started doing multiplication in second grade? I don't know, whenever you start doing multiplication, kindergarten, nursery school, when does that start?
Seventh grade.
What grade?
Second grade.
Second grade? All right, I was right the first time, all right. But with vectors, when you multiply them, there's two different ways of multiplying them. There are dot products and there are cross products. The dot product you can recognize because there's a dot. The cross product is a cross. Okay, not a Christian cross, it's just, an X. So if I have a vector A cross B, that's a cross product, this is a dot product.